Hello, chemistry students. Here we go with another video dealing with the gas laws. Today we have Charles' law. The biggest difference is that Charles' law shows a direct proportions graph as straight lines, which will be our biggest mathematical difference today. So here we go, Charles' law.
For a gas, temperature and volume are directly proportional. Keeping everything else constant, as the temperature of a gas goes up, its volume goes up. As the temperature of a gas goes down, its volume goes down. If you heat up a gas, it expands. The gas particles move faster, and they take up more space. Imagine a balloon that expands when gas particles bang against the sides. By expanding, that keeps the pressure constant. The faster the gas particles move, the more they will push on the sides of the balloon, expanding it. If, on the other hand, you cool the gas down, you put your balloon on ice, that slows the particles of gas down, so the balloon will contract. Jacques Charles is credited with this gas law relating temperature and volume, although he didn't publish it. He may have been too busy taking rides in hot air balloons. A colleague, Joseph Louis Gay-Lussac, published it, and very honorably gave Charles credit. Charles's law says that for a given amount of gas at fixed pressure, volume and temperature are directly proportional. V is proportional to T. You can write this mathematically as V equals kT, where V equals volume, T equals temperature in Kelvin, and K is a proportionality constant. We can rearrange this equation so it reads V over T equals K, or the ratio of volume to temperature is a constant, K. Very often, Charles' law is used to compare two situations, a before and an after. In that case, you can say V1 over T1 equals K and V2 over T2 equals K, so you can write Charles' law as V1 over T1 equals V2 over T2. Let's see an example.
So before we do the example, it's important to note that we need to keep the before and after conditions separate from each other. While there are several ways to set a proportion correctly, this is the easiest way to make sure the proportions get set up the right way. Just a reminder, we can do proportions using strict algebra, or we can use the shortcut, which is cross multiplying and dividing. Keep that in mind as you look at them solve things also.
A hot air balloon has a volume of 2,800 meters cubed at 99 degrees Celsius. What is the volume if the air cools to 80 degrees Celsius? We'll write Charles' law in the before and after form. V1 over T1 equals V2 over T2. We substitute in what we know. Remember, we have to convert temperatures to Kelvin. Kelvin equals degrees Celsius plus 273.15. So now T1 equals 372.15 Kelvin, and T2 equals 353.15 Kelvin. 2,800 meters cubed divided by 372.15 Kelvin equals V2 over 353.15 Kelvin. Solve for V2. Multiply both sides by 353.15 Kelvin. 353.15 Kelvin times 2,800 meters cubed divided by 372.15 Kelvin equals V2. V2 equals 2,657 meters cubed. Here's another example. At 0 degrees Celsius, a gas occupies 22.4 liters. How hot must the gas be, in Celsius, to reach a volume of 25.0 liters? V1 over T1 equals V2 over T2. Remember, we have to convert temperatures to Kelvin. Kelvin equals degrees Celsius plus 273.15, so T1 equals 273.15 Kelvin. Substituting in what we know, 22.4 liters over 273.15 Kelvin equals 25.0 liters divided by T2. Solve for T2. I like to cross-multiply here. 22.4 liters times T2 equals 273.15 Kelvin times 25.0 liters. T2 equals 273.15 Kelvin times 25.0 liters divided by 22.4 liters. T2 equals 304.9 Kelvin. Convert to degrees Celsius. Celsius equals Kelvin minus 273.15. So T2 equals 31.7 degrees Celsius. Charles' law relates temperature and volume for a gas, but there are other gas laws which relate the other essential variables associated with a gas. Boyle.
So basically, we have talked about Boyle's law, but talking about the Cayley-Sachs law. We'll be talking about the combined gas laws. So all these things will come into play later as we go through each lesson. That is it for today. You may log out unless you want to watch me try to save this thing.